up to the expectations of scientists, researchers who selected our symposium to present their research findings. This year, we have selected over 120 papers from more than 150 submissions despite delays and various setbacks due to the prevailing COVID-19 pandemic situation. We are compelled to conduct this symposium virtually this year, and it is a new experience for our organizers. Our faculty's vision is to make ISAE an annual meeting place for scientists and professionals in agricultural, environmental, and allied sciences to share their research findings, innovative ideas, and forge new collaborations. The broad theme of this year's symposium is Challenges in Agriculture, Impacts, Resilience, and Adaptation for Sustainability, highlighting the need of new strategies for agricultural and environmental management for enhanced productivity and to ensure prudent use of biological resources to sustain a healthy population on planet Earth. As we all know, networking in research is pivotal for the advancement of science and technology, and hopefully the presentations done and discussions followed at the ISAE 2021 would lead to further research and development of technologies and collaborations towards development and change in the quality of lives of people. I take this opportunity to express my sincere gratitude to all my colleagues of the organizing committee who devoted their time and energy to make this event a success. Finally, I would like to wish all invited speakers, special guests, authors, participants, a productive and pleasant virtual stay at the ISAE 2021. So we are looking forward to seeing you again in ISAE 2022. Hopefully, we would be able to have that event physically or at least in hybrid mode. So let me thank once again for those who have joined this symposium this morning virtually. And let me also thank the organizers for giving me this opportunity to address this international symposium. Thank you very much.
Thank you very much, sir. I am profusely elated to take an opportunity to introduce our chief guest of the day, Honorable Minister of Environment, Sri Lanka, Mr. Mahinda Amaravira, as the chief guest for ISAE 2021. It is an honor to have you here with us today. Sir, with equal pleasure, I cordially invite you to address this respected gathering.
Good morning, Professor Sujeeva Amarase. Professor David Rawlins, the keynote speaker of the symposium. Distinguished guests, students, ladies and gentlemen. As the Minister of Environment, it is a pleasure to be the chief guest of this important event. International Symposium on Agriculture and Environment 2021, organized by the Faculty of Agriculture, University of Ruhuna. The theme selected for the symposium is timely and important. Today we are in a challenge era across pandemic diseases, climatic change, soil erosion, and biodiversity loss. Today the main challenge in agriculture is to produce safe and high quality food to cater the demand of the increase in population across the globe. Under such challenging environment, achieving the target is the most problematic fact to the farmers, researchers, manufacturers, policymakers, and environmentalists. Therefore, this kind of conference are very much important to present novel research findings in different sectors and improved agriculture in a challenging environment. In future, resource constraint over water, soil biodiversity and landfill will affect agriculture systems. Sustainable agro-ecosystems have positive impact on agriculture while unsustainable systems feedback to deplete these assets, leaving few for the future. Sustainable intensification of agriculture would increase yield without adverse environment impact. Health complications of food contamination with agrochemicals are now well known. The long list of such complications include the conditions as immediate as allergies and gastrointestinal disorders, and long-term consequences like asthma, cancer, and kidney disease. Therefore, researchers have to focus to investigate possible safe agricultural systems to minimize these problems while improving the agricultural production in sustainable manner. When we consider the SAARC region, the main possible challenge identified in agriculture is fluctuation of yield year by year, land fragmentation and ownership problems, labor problems, lack of technical knowledge to apply at farm level, and not properly arranged marketing systems for agricultural products. I hope this kind of symposia would help to bridge the gap between researchers and farmers and must be essentially addressed to minimize challenge in agriculture. Identified solutions to overcome the challenges are adapt and learn new technologies, invest for high farm productivity and stay resilient against global economic factors. The symposium will open intellectual minds towards analysis of the combined agricultural and environmental systems. Further, it provides a path to analyze the challenges in food security in this century as population grow and consumption pattern change. Scientists can promote a continuing dialogue among agricultural communities based on sustainable intensification of agriculture. I am sure with your participation, this symposium will be a success, and I take this opportunity to extend my gratitude to the academic and the non-academic staff for the effort you made in organizing this event during this difficult period. Thank you.
Thank you very much, sir. ISAE 2021 is privileged to be graced by the presence of Senior Professor Sujeeva Amarasena, the Vice Chancellor, University of Ruguna, who provides us with the unparalleled leadership and guidance in uplifting the university. It is with immense pleasure and respect I invite Senior Professor Sujeeva Amarasena to share his invaluable thoughts on this special occasion with us.
Thank you very much. Good morning to all of you. Honorable Minister, Mahinda Amarawe, Minister of Environment, Deputy Vice Chancellor, Deans, Faculty of Dean, Faculty of Agriculture and other Deans, academic staff members, members of the organizing committee, and members who are joining the conference online from Sri Lanka and elsewhere in the world. Let me apologize for the slight delay in my joining. I had some interviews fixed for this day and it went on for a little while. And now I have just made myself free. So let me also thank the organizing committee for inviting me to be to speak today on this important topic of challenges in agriculture, impact, resilience, and adaptation for sustainability. I think I am looking at this entire conference from that theme, and I would like to see that the challenges we might have to face due to various factors, which includes currently the COVID-19 and its impact on the workforce and the settings, organizations, and then climate change, issues of fertilizer and so on and so forth, which are having a great impact onto our agricultural sector, not only in Sri Lanka but in the entire world. And I hope this conference will be providing some answers to some of the problems that we are going to face in the future. I think at the end of the day, agriculture should be looked at from the point of view of food security. Food security for everybody everywhere in the world, not just Sri Lanka, but certainly people in Southeast Asia, India, Nepal, Pakistan, Bangladesh, the poorer countries, and the whole of Africa, because we think the African continent is suffering more from food shortages and insecurity than rest of the world. So how do we provide food for everybody? Through agricultural products development and agriculture adapting itself to changes in climate and other factors. So we need to be resilient in adapting ourselves to these changes and look forward for innovative methods of increasing food production while maintaining the safety of the food. Because I think now something that we started in 1960s like non-organic fertilizer is now supposed to cause problems for health. Now that has to be overcome during the next decade at least, or maybe so. I think if that can be done, it's something that we could boast about as an achievement in the agricultural sector. The environmental issues that we are facing, rising temperatures, huge rains time to time, even these days. I think some of the farmers in Sri Lanka are having serious problems due to massive rains in some parts of the country. And their products, their plant growths and plantations are suffering with destruction or compromised outcomes. Now, it's not something that we can control, but can we control our agricultural growths and plantation, whatever, to ensure that these plants are resistant to such dramatic changes in environment. We do have an issue about changes in our environment and our own health at the moment. We have known about greenhouse gases for ages, maybe good 50 years now. But yet we have not been able to overcome the challenges of these problems yet. We had a serious issue about the ozone layer, and I think during COVID-19 pandemic, we saw, at least there were some reports, that the ozone layer is recovering when the greenhouse gas emissions were lowered and temperatures were not rising due to activity, human activity. Now, that's something that we can learn about and also develop and see whether we could do research on that, on how to reduce the damage. So in the similar way, the agriculture needs to get adapted. I think the traditional agriculture certainly need to change towards more technology driven, environmentally friendly, sustainable agriculture with increased production and yields. I have seen that it is possible during my short tenure as Vice Chancellor. Although I don't have a background in agriculture, I have learned from many of my friends in the Faculty of Agriculture that these are possible. and possible with relatively low costs and low investments. It's just that we need to change our mindsets and commit ourselves to change those so that the entire country benefits and the entire world benefits with such technology driven advances in agriculture and increase productions and ultimately reduces food insecurity. Now, I would like to see all who are present in this audience today to rethink about that kind of a strategy that will help the entire world overcome the issues of food insecurity in a shorter period of time once the COVID-19 pandemic is over. And I'm sure the COVID-19 pandemic would be over at some point, perhaps not maybe within the next few weeks, but certainly months, not years. So I think our intellectual contributions should be developed and directed towards that kind of approach to agricultural development in the post COVID-19 development drive. And if I can get that message across to all the entire audience, and if the audience could rethink about this challenge in the post COVID-19 period, because I think whatever that COVID-19 does will do, and it will disappear within few months, so that at least we can catch up with pre-COVID-19 situation and then rapidly develop again and try and see whether we could face pandemics in a better way than this, especially with regard to food insecurity in the future, maybe in another 10, 20, 30, 40, 50 or 100 years time. Because otherwise we will be still talking about the things that happened in Spanish flu pandemic and what happened in World War II and what would happen and what happened in COVID-19 pandemic, and again with the next pandemic of some other virus or some other bacteria. So that's my message to all of you. Please rethink about agricultural development in adapting itself to challenges both in the environment and also others like health and disaster, and adapting itself to provide adequate food to the entire world. Because we must never think of people like Sri Lankans. So we are all global citizens today. You can see that how COVID-19 is affecting everybody from US to other countries, poor countries in the rest of the world, and everybody is suffering. So we need to think like global citizens today, not Sri Lankans, and we need to resolve issues of food insecurity in the entire world, and it's not necessarily Sri Lanka. And then Sri Lanka would be only part of it, and I think we can definitely achieve these targets. So let me once again thank all the organizing committee members and Faculty of Agriculture for organizing this event, and thank all in the entire audience, and wish the entire conference all the success. Thank you. I'll be here for the conference for a short period of time, but I think I will have to leave a little early and then join the rest of the work of the day. Thank you.
Thank you very much, sir. The next dignitary to honor us with his presence is the keynote speaker for the inaugural session of ISAE 2021, Professor David Rawlings, Queensland University of Technology, Australia. May I now kindly invite Senior Professor S.D. Vanniyarachi, Dean, Faculty of Agriculture, University of Ruhuna, to introduce the keynote speaker.
Professor David Rawlings of the School of Biology and Environmental Science, Faculty of Science, Queensland University of Technology, Australia. Professor Rawlings is a soil scientist in the Sustainable Agriculture Program at the Centre for Agriculture and Bioeconomy at the Queensland University of Technology, Australia. His research sits at the nexus of the environmental and agricultural science, enabling high-impact research outcomes that benefit both fields of positive global change and food security. He specializes in the development and utilization of improved sensing and monitoring technologies for mitigating environmental greenhouse gases, improving crop fertilizer use efficiency, and monitoring soil carbon, reactive nitrogen, and biogeochemical processes. His work spans the Australian beef, dairy, grains, and sugar and horticulture industries, and he has worked internationally across Sri Lanka, India, North and South America, and New Zealand in cropping, dairy and rice systems. Working with farmers, state governments, the composting industry, and the researchers across Australia, he currently leads the National Smart Farming Partnerships project on unlocking the true value of organic soil amendments to develop a farm-ready tool for the effective management of compost into farm fertilizer budgets for environmental, soil health, and economic sustainability. With that introduction, very brief introduction, let me now invite Professor David Rawlings from the Queensland University of Technology, Australia, to deliver his keynote address. Thank you.
Thank you very much. Can you all hear me okay?
Yes.
Okay, excellent. So thank you very much for that very thorough introduction. Yes, I have been to your beautiful campus there, and I spent some time touring around southern Sri Lanka working with Inaugural, and it's certainly a beautiful part of the world, and I can only hope that we can get back there soon. So in these current conditions, it's sort of something we can all wish for is a speedy return to normal. So yeah, thanks again for inviting me to give this talk. I suppose what we're sort of talking about in this this conference and in general is around, how can we basically move forward with our current environmental, food security issues in a changing world, turning up the heat on our soil and water resources. We're looking at some pretty serious issues around climate change, and at the same time, we have to try and feed 10 billion people. So it's certainly a challenge. So all you young and budding and experienced and everyone working in this field certainly has their work cut out for them. So thank you very much for the invite, and let's get started. If I can figure out how to work my screen. All right, so when we sort of analogize this question, there's a great article written by Charles Mann. It was published in The Atlantic a few years ago. This is a sort of, this is the link to it down the bottom of the screen there. So it basically summarized, I suppose, science and scientific thinking into two streams of thought, particularly around what he called wizards versus prophets. And this is coming back to how do we basically look at addressing this problem? How do we actually feed the world? How can we feed 10 billion people, particularly in a case now where we've run out of agricultural resources? We're pushing planetary boundaries as far as climate change, biodiversity loss, nutrient inputs, and we're also hitting yield plateaus. And so we really we sort of have these two schools of thought about how we can actually do that. And it's basically exemplified by, on the left, we have William Vogt, the father of the modern environmental movement, basically looking at the trade-off between environmentalism versus affluence, and particularly from a Western world's point of view. Obviously, there's a lot of waste in our agricultural systems, and that comes at a detriment to the environment. And the other side of that coin, on the prophets, is the Norman Borlaug, the father of the Green Revolution, technology-driven ideas around how can we actually improve crop yields, improve agronomic practices to try and boost yields and technologically advance our way out of this scenario. And unfortunately, in the past, a lot of the agricultural research, I suppose, has really fallen into one of those two camps, and they haven't really worked together. And so the challenge of future scientists is we can't work in isolation anymore. We can't work in our silos. We can't be either a wizard or a prophet. We have to be both. And a lot of the work we're doing now, particularly work that Anouk has been doing over in Sri Lanka, what we're doing in Australia, what we were doing in India at ICRISAT, which is one of the homes of the Green Revolution. We're looking at how do we integrate these two systems, bringing in the technology, but also looking at this environmental sustainability. So a bit of a snapshot, I suppose, of where we're at with our agricultural production globally and how did we get there. We're looking at, we already utilize a fair chunk of the planet around, our food production. We're looking at 12% of the planet is taken up for crops, and this is of the land area, and another further 26% for pastures, mainly extensive beef grazing pastures or livestock. And that's really at a maximum. There's not a lot more land we can add to that. We've got some natural areas, we've got some forest, and then we've got a lot of basically unutilizable land around deserts or polar regions or whatnot. But if you look at this graph here and the red line at the top, that's our population growth over the last 50 odd years. We've done well. We've managed to increase our yields. So each of those blue lines is a crop yield in tonnes per hectare. And as you can see, starting from the 1960s, we've more than trebled the yields, and this is through agricultural advances, particularly in agronomy and fertilizers and breeding. And so we're basically currently feeding a world population and producing 12.8 billion tonnes of grain annually. All right, that's fantastic. We're doing a pretty good job there. Let's see how we go in the future. So moving forward, we're now looking at a scenario where we're going to hit by 2050 just shy of 10 billion people. So we have to feed an extra 3 billion odd people, and we have to produce by 2050 5 billion tonnes. So we're going to increase our global food production from 2.8 billion tonnes to 5 billion tonnes. And so if we actually look at the yield required to meet that global demand, by 2050, we got maize, we got rice in the green, we got wheat in the black, and we got soybean in the blue, dark blue. How are we actually going to get there? Unfortunately, if you look at where we need to be, and we need to be basically up where that blue arrow is, and where we're projected to get based on our current trajectory, and this is actually not even accounting for some of the recent declines in crop yields we've actually been seeing, we're still going to be 2.5 million tonnes a hectare short. 2.5 tonnes a hectare short for maize, 2 tonnes a hectare short for rice, 1.1 tonnes a hectare short for wheat, and 1.5 tonnes a hectare short for soybeans. And that's even assuming best case scenarios and not taking into account the effects of climate change. So all this means if global population growth keeps on continuing at the current level, we're going to be 1.2 billion tonnes of grain short. And that's a pretty scary scenario. There are some easy wins around reducing waste, and there's a lot of food waste, particularly in the Western world. So, there's some sort of movements to be had there. A lot of the feed goes to livestock, which is argued, could be better used, I suppose, or, if we do run into shortcomings, there's potential for movement there. But, there's 1.2 billion tonnes. We've got to somehow produce an extra 1.2 billion tonnes of grain on top of our current trajectories. And so that's the challenge facing us, our agricultural systems and our agronomists of the future. So taking a step back to, well, what's come before, we start with Norman Borlaug from basically also known as the father of the Green Revolution. Started a lot of his work at CIMMYT, the International Wheat Research Organisation in Mexico. We've worked quite a lot in ICRISAT, which is the dryland partner of CIMMYT in India, in Hyderabad. And there's a few of these other places around the world, IRI, which is the International Rice Institute in the Philippines. Historically, looking at crop production, so this is now total crop production in billions of tonnes. We've made some pretty good ground early on through the Green Revolution. This is where Norman Borlaug did his work, improving plant breeding, improving fertiliser rates and fertiliser requirements, basic agronomic practices, and that really made a big difference to grain yields and really boosted them around the world. Better varieties and better agronomy, basically. The next step was, well, if we actually look at land area, and that's what the red line is actually how much land area is now going under agricultural production. We see this big jump in our land area around 1980, and that's called the extensification. So from 1980s to sort of the 2000s, we didn't actually improve our crop yields that much on a per hectare basis, but a lot of the gains we made were around just farming more land and bringing land in production, which we didn't see before. So unfortunately, but when we look at where we need to be, and if we extend that graph out to 2050 and look at those 1.2 billion tonnes, okay, we need to go where that straight line, blue line is going. That's where we need to get to with our crop yields. But we've now run out of land, so we can't just go and actually bring in more land in production. We've sort of reached our planetary boundary for arable land, good quality land, and obviously, you know, taking into account biodiversity loss and climate change, you know, we've probably taken out too much land. So we've got this challenge where we can't rely exactly on what we've done in the past to get us into the future. We need to start looking a bit more differently, I suppose, and looking at the other aspects. So what we need 1.2 billion tonnes of grain and with no additional land. But we've done well feeding the world so far, but it's come at a cost. We've exceeded our planetary boundaries, and this is a concept that was sort of released by the Stockholm Resilience Centre back in 2009, where it looks at, well, what can our planet sustainably handle as far as these impacts that we're having, particularly for our food production. And as you can see, where we need to be on this globe here is what they consider, based on scientific observation, these safe boundaries, these safe planetary boundaries, are in the green. And as you can see, you know, that's basically, we've used the equivalent of 10 planets worth of biodiversity loss. So we're way out of our sustainability limits for biodiversity loss. The nitrogen cycle, we're over 5 planets worth of the nitrogen cycle. That's how much additional nitrogen we've been putting into our systems. And that's, you know, coming back to that, our Norman Borlaug sort of techno-driven philosophy of just put more nitrogen, put more nutrients on. It's come at a cost. We're now hitting peak nitrogen. And of course, underlying all this stuff is the climate crisis around climate change and the effects it's going to have on global temperatures and climatic variability. And these are just a few of the trends that we've seen. You know, that food production line going up from 1960 is mirrored across a whole range of different metrics, whether it's greenhouse gases, carbon dioxide, nitrous oxide, methane, whether it's ozone, temperature, ocean acidification, nitrogen in the coastal zones, tropical forest loss. So we've managed to feed the world, but it's come at a pretty big cost. Climate change, as I mentioned, is going to be the big one. This figure on the right here sort of summarizes where we're at and where we need to be to basically hit our aspirational goals, which are 1.5 degrees warming. And as you can see, the Paris goal is down the bottom here. Where our current targets are got nowhere near that. So, you know, agriculture plays an important role in climate change. It's also got a very important role in mitigating climate change. And we basically need to push our systems harder, to make sure that we can actually stay within these planetary boundaries for climate change. And even if the optimistic targets, we're still looking at a 2-degree increase in climate change, which can be pretty catastrophic depending on where you are. This is a busy graph, but it basically summarizes agriculture's contribution to climate change, and it's small at the moment, and that's an important aspect to take away. That we're only accounting for about 20% between agriculture and land use change of global greenhouse gas emissions. The bulk of the emissions are still coming from energy, but I suppose the consideration here is that as alternate energy sources like solar and wind become more widely uptaken, that proportion of agriculture is going to grow. So it's going to become more important in the future. It's the key source of nitrous oxide at the moment. It's a very big contributor to methane, and both of them are associated with our livestock and our fertilizer nitrogen systems. So you can sort of see the majority of our nitrous oxide is actually coming from agricultural soils, and that's associated with the nitrogen fertilizer we put on. And this is basically a summary of those sinks and sources of nitrogen. I'm not going to go of greenhouse gases. Sorry, I'm not going to go into it in too much detail, but we basically have methane coming off from rice. It's an important greenhouse gas. Nitrous oxide coming from our fertilizer, nitrogen fertilizer inputs we put in, and also from animal manures. We do have soil carbon, so soil carbon can be sequestered through management change as well, so we can obviously offset some of our emissions, and obviously land clearing releases CO2 back into the atmosphere. So agriculture is a very important role in climate change, but with mechanisms such as potentially increasing soil carbon sequestration and also reducing methane and nitrous oxide emission, it also gives agriculture a fantastic opportunity to be involved at the forefront of mitigating climate change. And when we talk about climate change, and particularly that impact that agriculture has on it, we basically need to be able to summarize those three greenhouse gases together to just look at the whole impact of the system. So you can't just look at carbon, you also need to consider the nitrous oxide, and you also need to consider methane. And we do that through this term called CO2 equivalence. So basically, the equation works as one CO2 is equivalent to one CO2. I mean, that's one CO2 equivalent, relatively straightforward. Methane, which has got a higher radiative forcing, so it traps more heat in the atmosphere, it's actually equivalent to 25 CO2. So one molecule of methane is equivalent to 25 molecules of CO2 as far as its global warming potential goes, or how much heat it traps in the atmosphere. But if we look at nitrous oxide is actually worth 265 times more than CO2 on a per molecule basis. So if we're emitting 1 kilogram of nitrous oxide for every, say, management change we do, we might be looking at applying manures to sequester soil carbon, but if we're actually emitting nitrous oxide, just 1 kilogram of nitrous oxide will offset over 265 kilograms of CO2. So it's very important that we capture all these three gases for whatever management change we're proposing to look at climate change. You can't just look at them in isolation. And this is basically the equation is the CO2 plus the methane times the 25 plus the nitrous oxide times the 265, and you sum them all together and you get this CO2 equivalence. So I mentioned nitrogen before, and it's a really tricky one. The nitrogen dilemma, it's a very important nutrient. It's essential for plant growth. I mean, we know this is data from Inaugural research, actually in southern Sri Lanka there, where we know that putting on nitrogen increases yields. I mean, it's sort of agronomy 101. And that's basically led to this huge increase in nitrogen inputs. And this is why we've now exceeded our planetary boundaries, because one of the simplest things you do to increase yields is put on more fertilizer. However, it's got to the point where we're now putting on too much fertilizer. And particularly in southern and eastern Asia, where they're basically it's more than doubled. The amount of fertilizer being put on has actually doubled since 1990. And that fertilizer, it's a very important element, but it's also a very leaky element. It's leaking out of the system, and it's causing major issues of groundwater contamination and climate change. And this is what happens when we get it wrong. Basically, if we can get good yields to a point, but once we get put on too much nitrogen, basically we're not seeing any additional yields. We're running into other nutrient limitations or water limitations. But what happens then is our losses then increase exponentially, and we get this nitrous oxide being emitted. And this is nitrous oxide coming off here following the application of chicken manure. So can we, this planet, feed 10 billion people? Well, hopefully, but it does require us bringing the wizards and the prophets together. We need to evaluate environmental costs of agronomic practices. We can't look at just agronomic improvements in isolation, but we also need to consider the agronomic and economic costs of environmental measures. So there's no point proposing a great environmental measure that will reduce emissions, but it's uneconomical because it's just never going to be taken up. But the good thing is, all of the time, these are win-win situations, so we can basically win both ways. And we can get low carbon agriculture. We just need to do the research, and this is where you guys come in. We need to baseline our current agricultural practices. This is a figure from some of Inuga's research there, just looking at, well, what are the emission factors, or how much of our nitrogen that we're putting on is actually being lost as nitrous oxide. And then we need to start assessing alternative nitrogen practices. We need to look at the yield, but we also need to look at the carbon footprint, and we need to look at the economics. We need to look at those three things, not in isolation. And technology has a role, absolutely. So one of the big things that our group has done is develop these automated chambers for monitoring, for making the monitoring of these greenhouse gases easier. These are measuring methane and rice, measuring nitrous oxide in the US. And this is in one of our systems published in Journal of Environmental Quality from Australia. And basically what it allows us to do is get high resolution, high quality data to really basically hone in on those management changes that are effective at reducing greenhouse gas emissions. We also look at carbon, so we can measure carbon using things like these eddy covariance flux towers. Once again, we're looking at a technological solution to an environmental issue. Basically gives us really good information around our carbon sequestrations. This is in a grazed pasture rangelands in southern Queensland, where I'm from. Gives us a lot of information, and we can really tease out the effects of our management that it has on the impact of climate, and but also look at the yield production and the economics at the same time. And these economic trade-offs are ultimately what's going to drive all this. We got to have practice changes that are economically viable, so that we get farmers to uptake them. We can't really just rely on government incentives and big sticks through regulation. And it's important to get the messages out there that, you know, sometimes what might sound useful is actually not going to be that economically viable. Once again, more research from Inuga's stuff there, where we look at, on the left-hand side here, we've got looking at input costs for basically fertilizer, whether it's organic fertilizer through compost or synthetic fertilizer through just urea. And we're looking at the cost per kilogram of grain produced. And as you can see, in the green and the blue, this is how much synthetic fertilizer costs. So we're basically, our input costs are below basically $5 or 5 rupees. Whereas we look at the cost associated with the compost, and we're sort of 10 times that. So the best sounding solution as far as something like compost goes is not always the economic solution. But we can actually tease these with more information and more data. We can tease these nuances out and find the cases where, well, it does actually work. And this is some work that we did in Queensland, where I'm from, where we compared different compost sources. So we got chicken manure down here versus feedlot manure down here. We got how much emissions are being reduced, being emitted on this graph, and how much it costs on this axis. And you can see the best actual scenario is the chicken manure, and it's much better than this one, which is the conventional urea. So we have a win as far as no additional greenhouse gas emissions, but a lot lower cost, and that's a win-win for both. And then, of course, there's other ones that are not so easy to quantify. So if we look at applying litter for instance, or, you know, just things on soil health. These are not so easy to quantify, but they're still nevertheless so important. And this is a figure I show around the impact of retaining mulch. And as you can see, the frame on the left-hand side there, lots of surface sealing, no litter, big rain splash erosion, lots of displaced soil, lots of, you know, potential surface sealing, clogging up of macropores, big issues with soil structure. When the litter's been left on, in this one over here, you can see some nice big aggregates, some really nice infiltration rates, and pores in the soil, lots of life in that soil. So these are things that are really, really important for agricultural production systems, but not so easy to quantify. And the same with greenhouse gases. So in a system that's not healthy soil, we're going to have a lot of nitrous oxide come off. We're going to lose a lot of our fertilizer through anaerobic processes, and we're going to get a lot of methane being reduced. And compared to a nice, healthy soil, those losses are going to be much lower. So I suppose I'll just finish on one more positive note, I suppose. And you might have noticed when I talked about this graph before that I didn't include that last section here. This is highlighted by this green arrow here. But this is actually what's happened through conservation agriculture. So we're well on this path already. We're sort of improving our environmental impacts as well as increasing our food production. So we just need to keep this trajectory. It's not all a lost cause. This is a great demonstration that we can actually do it, but we just have to work together. And I'll leave with these two sort of contrasting quotes around really what is essentially organic farming versus, I suppose, the more techno farming aspects. And it's very interesting concepts on both. So with that, I'll say thank you, and it was a pleasure talking to you all.
Thank you very much, sir, for your invaluable words and for enlightening our minds with new insights for future research in sustainable agriculture. It is with immense contribution of many, today's event has been made possible. Many people have worked hard for the success of ISAE 2021, and they truly deserve a sincere appreciation. So, it's my pleasure to invite Professor Dalsi Senaratne, Secretary, ISAE 2021, to deliver the vote of thanks.
Good morning, distinguished guests, ladies and gentlemen. Today, I have been conferred the opportunity to deliver the vote of thanks as the Secretary of ISAE 2021. I find it a great honor and privilege to me. On behalf of the organizing committee, first and foremost, allow me to express our heartiest gratitude to Honorable Minister Mahinda Amaravira, Minister of Environment, for accepting our invitation and joining the conference. We found your presence at this special event of the Faculty of Agriculture, University of Ruhuna, is a great honor to us. Thank you very much indeed for your participation. Professor David Rawlings from School of Biology and Environmental Science, Faculty of Science and Engineering, Queensland University of Technology, Australia. I am sure that the participants witnessed that you have delivered a timely, important, and valuable presentation on the theme of the year symposium. Organizing committee of the symposium and the participants here are indebted to you for accepting our invitation and joining the event to enlighten with your latest knowledge and experience. Sir, it's an honor to have your keynote speech today, and thank you very much for your invaluable contribution for the success of this event. Ladies and gentlemen, next, I would like to acknowledge Senior Professor Sujiva Amarasena, Vice Chancellor of University of Ruhuna. Sir, you have always been with us. You are the strength, and the guiding light in any endeavor we step onto. Your contribution in organizing ISAE 2021 is indispensable. Thank you very much, sir, for your participation. I would like to thank Professor Saman Chandana, Deputy Vice Chancellor of University of Ruhuna. Sir, your presence added a glamour to our symposium. Thank you for accepting our invitation and joining the event. Senior Professor S.D. Vanyarachi, the Dean of the Faculty of Agriculture, University of Ruhuna. Sir, you made an enormous contribution to the success of ISAE 2021 by being with us throughout the organizing process as an advisor, leader, and a part of the team. Please accept our sincere gratitude, sir. At the same time, deans of other faculties, council members of University of Ruhuna, all academic staff members of University of Ruhuna, registrar, and all the non-academic staff members for accepting our invitation and brightening up the event by joining online. Today, you will have the opportunity to witness the latest research findings, new thoughts, and experience of eminent figures of different sessions come under 6 thematic areas. Professor Yasushi Mori, School of Environment and Life Science, Okahama University, Japan. Professor Kuroki, Graduate School of Agriculture Science, Kobe University, Japan. Dr. Ali Fakir, Faculty of Agriculture, Bangladesh Agriculture University. Professor Kabir, Bangladesh Agriculture University. Professor Toyama, Faculty of Agriculture, University of Ryukyus, Okinawa, Japan. Sirs, thank you very much for accepting our invitation and sharing your knowledge and experience with us. We are indeed privileged to have you here. All the chairpersons of today's conference, madams, sirs, we really appreciate your enthusiasm in chairing sessions towards the success of ISAE 2021, and thank you very much. Also, session conveners assigned to different technical sessions are acknowledged for taking up responsibilities. Accepting our invitation, number of local and foreign invitees are attending this event today. There's no doubt that your participation added a great value to this event. Please accept our sincere gratitude. Our authors and the presenters of the scientific sessions, you and your scientific work have enlightened the symposium. You have submitted wide array of research findings which support our theme this year. Thank you very much for your cooperation, and you will be with us in the coming years as well. This year, ISAE is the first virtual conference conducted by our faculty across the barriers of the prevailing pandemic situation. Therefore, the support given by the staff of the computer unit of the Faculty of Agriculture is highly appreciated. This is a team effort. There are many academic staff members, those who were extended their fullest support in numerous ways. Though I did not mention their names separately, all the supported academic staff who served under different committees are hereby deeply acknowledged. Temporary academic staff members and non-academic staff members are also acknowledged for their timely, important involvements. I wish you all will enjoy and experience intellectually ISAE 2021 in a comfortable manner via Zoom. Hope to see you once again in year 2022 symposium as the coordinator ISAE 2022. Thank you.
Thank you, Madam. Ladies and gentlemen, we have come to the end of the inaugural session of ISAE 2021. We will conclude the session now. Please be silent and pay respect to our national anthem. Scientific sessions will be commenced at 10:45 a.m. Please log into the Zoom invitation link relevant to your sessions on time. Thank you very much for joining us today. Hope you will have a fruitful day with ISAE 2021.